Mm, Hello, everyone. Thank you for joining this presentation. I'm Yu Kim of KIST, and I've been presenting in the APRP working group regarding wireless and data center communication technologies. Pardon?
Yes, go ahead.
Yeah. Today, I'm going to introduce inter-data center RDMA technologies to you. Now, let's begin. At the last APRP sessions, I introduced you the index project of KIST. Index project is the data exchange network node. I explained the concept of data exchange node by comparing it with the existing internet exchange system. In the left figure, the large-scale data traffic, such as raw data for AI training, causes significant bottlenecks when passing through IXPs, leading to congestion and reduced service quality. On the other hand, in the figure on the right, the data exchange nodes do not handle regular internet traffic, unlike IXP. Instead, the data exchange node links various data networks directly to ensure fast and secure data transfers. This is particularly crucial for research data, which can be very large and sensitive. Another advantage of this structure is that it can be physically separated from the internet network, thereby reducing the risk of the security attacks. I also briefly introduced the TCP BBR. BBR is a congestion control algorithm developed by Google, and it is designed as a modification of traditional TCP congestion control to better suit data center environments. I researched TCP BBR as one of the technical considerations for inter-data center transmissions in the index environment. As a data exchange node rather than an internet exchange node, index is required to handle large-scale traffic between data centers, not public internet traffic. In addition, since it is used by a relatively small number of large-scale endpoints, the traffic pattern is expected to be burst rather than steady. This occurrence of large volume burst traffic in short periods is similar to the challenges faced by recent GPU networks. Therefore, we are exploring various methods to manage situations where a large amount of traffic suddenly occurs between data centers conducted through the index network. One of these methods, which we presented previously, was BBR swept, introducing congestion control at the TCP level. In this session, I will introduce another scenario assuming RDMA connections between data centers, and I will share our research findings on the efficient transmission of bursted RDMA traffic. Let me start by explaining what RDMA is. RDMA is remote direct memory access. RDMA concept was introduced in the VIA, Virtual Interface Architecture, network abstraction model. In traditional networks, protocol stacks were implemented in software within the host kernel. As a result, this imposed a processing burden on the CPU and became a bottleneck when there was a need to handle large volume of data at high speed. To improve performance issues such as bandwidth, latency, and CPU load, the VIA, the Virtual Interface Architecture, was proposed. The VIA is a network abstraction model designed to enhance performance by supporting RDMA, which enables direct access to the memory of a remote node, and zero copy, which minimizes buffer-to-buffer copying. So RDMA minimizes CPU involvement to enable fast and efficient data transfers. And there are several RDMA technologies. First, InfiniBand is a high-performance interconnect technology primarily used in supercomputers and data centers, offering high bandwidth and low latency. It requires dedicated switches and network interface cards, comes at a high cost, and operates within a closed ecosystem. And the ROCE, IDMA over Converged Ethernet, is a technology developed to address one of InfiniBand's main drawback, the requirement for dedicated switches. The ROCE enables high bandwidth and low latency RDMA data transfer over Ethernet networks while offering performance comparable to InfiniBand. With ROCE, we can use standard Ethernet switches, then it's possible to build a network at a much lower cost than InfiniBand network. From a technical perspective, ROCE version 1 replaces InfiniBand's layer 2 header, the local routing header, with an Ethernet header. This allows the use of standard Ethernet switches, but also introduces certain limitations, such as having to adhere to Ethernet's 9,000 byte frame size limit and requiring additional mechanisms to ensure lossless transmission. And ROCE version 2 takes it a step further than V1 by replacing the layer 3 header, the global routing header, with IP-UDP headers. As a result, ROCE version 2 packet can serially pass through IP and travel WAN networks to reach other data centers. However, in practice, due to security and operational management issues, it is generally connected through tunneling between data centers rather than fully following IP routing protocol. Anyway, we can apply IDMA not only inside data centers, but also across inter-data center WAN network for reduced latency and improved throughput. However, it also introduces challenges such as network delay, packet loss, and security compared to usage within a data center. Here is an example case in which KIST participated. The KASI, Korea Astronomy and Space Science Institute, operates 4 observatories of the Korean VLBI network, KVN in Korea. Each observatory generates large volume of observational data, which are collected at a central data center via RDMA for analysis. The RDMA data is transmitted through CREONET, the research network operated by KIST. They tested memory-to-memory transfer performance using RDMA, and as shown below, achieved nearly full utilization of the 10 gigabit network capacity, averaging 9.86 gigabps. Although their actual data transfers, not just testing, showed slightly lower performance at around 8 gigabps due to disk I/O limitations, the results still demonstrated sufficiently high performance over a physical network distance of approximately 400 kilometers away. And this is some kind of research. Lastly, I would like to introduce a recent study related to RDMA flow control in inter-data center environment. As mentioned earlier, in the process of adapting InfiniBand's network stack to an Ethernet-based environment, ROC requires additional mechanisms to ensure a lossless network. To achieve this, the technology called PFC, priority-based flow control, is used as a fundamental flow control mechanism for ROCE. PFC is selectively purges specific traffic clashes during congestion rather than halting all traffic. The PFC flow control operates by monitoring the ingress queue length of downstream ports. First, when the ingress queue length exceeds a predefined threshold XOFF, the downstream port sends a pause frame to the upstream port, instructing it to temporarily halt traffic for a specific priority class. This ensures that the buffer does not overflow, preventing packet loss. And when the queue length decreases below another threshold XON, the downstream port sends a resume frame to the upstream port, allowing the transmission to resume. It's very easy. And last, the difference between the total ingress buffer size and the XOFF threshold, their difference serves as headroom to accommodate packages that are already in transit, in-flight package. In this headroom is larger than the one of BDP, bandwidth delay product. It means the all pipe size, then the buffer overflow can be avoided. However, having a large headroom is not always better. The larger headroom makes the network utilization lower. In other words, it can be considered a tuning parameter that balances network efficiency and the risk of buffer overflow. Therefore, it is important to tune this value approximately. In this formula, to eliminate the risk of buffer overflow while also achieving maximum transmission efficiency, the buffer size ultimately needs to be as large as 2 times of BDP, bandwidth delayed product. The problem is that BDP increases when the BDP increases with longer transmission distances, meaning that when environment there are very long distance transmission, and BDP increases very high, and that means the required buffer size becomes impractically large. One study leverages the concept of virtual implied package, which is an estimated value of the current implied package, in addition to current queue length to control flow, aiming to achieve lower latency with less buffer usage than PFC. In addition to this, there have been many existing studies on RDMA flow control, but I included this example to highlight that recent research has started to consider RDMA transmission over WAN environments as well. I am personally interested in the issue and will continue to study it further. This is my next page. Today, I gave you a brief overview of our ongoing research on RDMA in inter-data center communication environments within a short time. Going forward, as part of the index project, I plan to continue exploring and presenting on topics related to large-scale research data transfer between data centers. Thank you for listening.
Okay. Thank you.
Yes, very small volume.
Thank you so much for your presentation. Anybody questions about that?
Working, this is Andrew. We did some work on extending the over intercontinental distances in our reference. There's a number of papers. One of them is in Cortex, and the other one is in 2.0. Some of the things we found were that it was more cost effective to actually use opportunistic caching to access data without having to move it around using the clusters. And we assumed at that time parity performance was semi-rich with a distributed system running over 4 different continents. So there's quite a lot of background work, but we will see you're actually running over TCP. And as you presented, BDR makes a significant difference in terms of the back-off and long-term performance duration of the data clusters. I'll be very happy to talk to you about this.
Thank you. Okay. Yes.
Sorry, the volume is very low.
It's just outside. Yes, anyway, the index project is depend on the PC and ClearNet, and the most of those technologies depend on the Korea domestic situation. We want to establish the inter-data center.
Yeah.
And we have a lot of data center, but just the standalone, just using and the commercial line, or even though they're using the research network, and the bandwidth is very mixed. Yeah. And not the dedicated and not the high throughput or high fast. So we are the one of the apply for the new TCP algorithm, or even though the InfiniBand, or the as the Andrew before mentioned before, and he already tested the intercity in the country.
Yes.
Was already yes. The last year you just tested the intercity intercountry.
Four continents, we've got two papers on it. It's called Infinity Cortex and Infinity Cloud.
Oh, remarkable.
Yeah.
Which country?
Australia, Singapore, the US, and Europe.
Oh yes. So how the performance the given bandwidth?
So we saw line rate performance
Yeah.
based on, so this was 10 gig circuits,
Yeah.
and it ran the circuits at 98% continuous utilization for 2 years. Like it was a flat line, 98% utilization in both directions.
80%.
98%.
980.
So it was compared to TCP, where you see it doing this, it was an absolute flat line.
That's remarkable. Yes, very dedicated. Yes.
This is a really good way to bridge InfiniBand clouds or InfiniBand fabrics across wide area networks. So excellent that you're doing work on Ethernet. That was the next thing we were going to actually look at. But we had dedicated InfiniBand extenders, which were horribly expensive. So if you can get this into a commodity system, really good value.
Okay, thank you for your comment. Thank you, Dr. Kim, for your presentation. Thank you.
Thank you.
Okay, they didn't hear our voice.
I'll send him some mail.
Yes, sir.
I'm happy to share our research so we can do the next phase.
Okay, okay. I want to introduce the next speaker, and Susma Date, Professor Susma Date. He came from this Osaka University, and he also in charge of Osaka University Supercomputing Center. And today he gonna talking about his Onion project. It means that is the such like is high bandwidth distributed HPC-like project, and he wanna update his activities and research areas.
Okay.
Yeah. In your pocket.
Okay. Who's the-
Okay, go ahead.
I'm Sukundatte from University. University of Osaka. So our university has changed the name of official name of university. So it used to be the Osaka University, but our university changed University of Osaka. So this is I'd like to introduce a little bit update of our Onion project. So basically, I'm working for the computing center at the University of Osaka, and I'm in charge of the procurement and the management of the supercomputer system. And I have responsibility to provide the high performance computing environment to the researchers in not only Osaka University but other university and other research institutions in Japan. And actually, I even to work for the other computing resources, but I'm not feeling that the aggregation of computer resources and data resources and network resources for the advancement of the recent academic research. And this is this slide shows what I want to do under my position. So I'm trying to collect, aggregate data from the data sources on the campuses to our data infrastructure named Onion. And after that, so the researchers as users can enjoy the high performance computer resources for their analysis and their computation. And maybe after the computation, they want to manage the data such as research results, measurement data in open science manner. And so that's why our research data infrastructure are now connecting to the Japanese research data management system provided by the NII, Japanese Research Institution, under the Ministry of Education in Japan. And we'd like to make the eco cycle of the research and data research and development. And today's talk is this part, so this part, high performance data. Sorry. And so data transfer services from the data sources on campus to our data aggregation infrastructure. And so let me introduce briefly what is Onion. So Onion is basically the storage system of the supercomputer system named Squid. So we are providing the supercomputer system named Squid. Squid is basically a heterogeneous cluster system of CPU and GPU and vector processor nodes. And for GPU, so we are providing the A100 in NVIDIA A100 GPU. I think in currently total number of the A100 is 360 something like that. So anyway, we have a lot of some. And the Onion is again so the storage system, and we are now providing the functionality to the researcher to allow the researchers to aggregate data from the several data sources to our aggregation, our storage system. And also we are providing the functionality of allowing the researchers to make the research result public to the researchers with the supercomputer system account. So anyway, Onion is so name again. Okay, so our name Onion is Osaka University Next Generation Infrastructure for Open Research and Open Innovation. This is Onion is acronym of this official name, and we just started this Onion project as a proof of concept. So this means that we may solve these services if users are not satisfied with these services. Maybe. So this is a very overview of the Onion system. The Onion is basically the three storage system. So and I will show later. But anyway, so this is the Onion part. So I'd like to provide the functionality of getting the data from the several data sources on the campuses to our supercomputer system, so that the supercomputer system utilization become high. And also currently many IoT devices are on campuses to get the several environmental data, and such data should be aggregated to our computing resources, so that people can immediately perform the data collected from the such sources. And also after the computation, so many of the supercomputer system users want to share the data to the research collaborators in the research institution overseas. And also sometimes people have their own storage system. So in the case the user want to connect the Onion storage system, so we provide such functionality. And also this is a very simple request, so that all the supercomputer system just provide command line interfaces for the data manipulation, and so that's why we provide the web interfaces. So Onion satisfies these requirements. And this is a very shows the internal structure of the Onion system. The Onion is basically the Nextcloud and the parallel files, exascaler as parallel file system, and Hyperstore and object storage. So we combine these three storage solutions using the AWS S3 protocol, and we provide such functionalities shown in the previous slide. And this is a very overview from the user perspective. The user can access this kind of very simple interface, web interface, and under the Nextcloud web interface, the several storage system can be integrated. So if you have their own laboratory web system, so that the system can be connected to our Onion system, and user can enjoy the single disk image of these device image. Okay, so now this is what is happening in Osaka University after providing Onion data aggregation infrastructure. So the researchers in the campuses are now trying to connect several scientific devices like this, including the microscope and a sequencer or anyways, or such things. And now that is connected to our Onion system through the measurement data aggregation and delivery system. This system is basically just deliver from the NASA server and connecting to the science devices to the Onion system gradually. So this is what is happening. And but one of the problem is performance. So we are just using the campus network for this system. So that's why people are just complaining performance is very bad, so very slow. So that's why we started a new project. So Red Onion project. Red Onion project is the short for the research enhanced Onion system. And this part is our computer center. So our center has a storage system and supercomputer system. And so So now, to tackle performance issues, so we are now working for the establishment of dedicated network to several department on campus, like the hospital and the research institute or something like that. And so that department provides a lot of data. And so this is currently working for. And so you know even if we connected high performance, high speed network from somewhere to somewhere, so we cannot get the performance. So that's why we try to develop the high speed data transfer technology. So this is the basic view. So this is the department, so on the campuses. And our center is located in the center, so every data should be transferred from to by its computing center. So if user want to put the data to our computing center, so data is synced to our supercomputing system. This is a very basic design. So anyway, so we now have already installed this system, half of the Red Onion. So this is actually this slide shows the equipment of the composing the Red Onion project. So this is the NVIDIA 200 gigabit network switch, and this is the data transfer node. So dedicated to the data transfer and receiving. And we have now created 4 DDM servers. And this is a parallel file system that can accommodate the data from the from data transfer node. And this is that's part of our computing center. This part. So now we are trying to install the other part. So I mean in the department. So this is the and so anyway, okay, so we are now, in the past, we tried to check the performance of the data transfer. But in supercomputing 2023, we connected the Denver to Japan and we tested. But in the case, so we couldn't get a good performance from this to this. Performance is, I think at the most, I think less than 55 gigabit throughput. So even if we use 100 gigabit, so that's why we try to we started the collaboration with several companies to get the better performance. So and we anyway soon we collaborate with Japanese company NEC and Clearing Technology and EDN storage vendor. And we by through the collaboration we configure and tune the network part and OS part and memory to this part. So anyway, this is and so again, so anyway, now we have installed the part of the economy to our computing center. And so I'd like to show some measurement results using the movie. So you can, I hope that you can feel that this performance is very good. Okay. So now my measurement test is like this. Okay. So data is located here, 1 terabyte data, and the data sent into from the one DPL node to the DP and to the other DPL node by a switch. Okay. So and data is stored to this. Okay. So that's this. Okay. So I'm hoping this. This is actually scopy. I'm just using the scopy command for the transfer. This is very slow. So the data is something like this. Okay, so very slow, but still, I think 8 gigabit something like that. Okay, so using the 100 gigabit network.
Between where to where?
To the so from here to here, this to this.
Internal.
Yeah, internal.
Yeah, okay,
And actually, this is connected to 200 gigabps.
right,
But actually, we
yeah,
save the traffic to the 100 gigabps because we are planning to set up the 100 gigabps dedicated network.
Mm.
Doesn't. So this is anyway. So this is a SCOP traffic. SCOP get transfer. This could be.
Can I just make a suggestion? During the data mover challenge, we found a product called MSCP developed by a PhD student, which is parallel SCP. So just swapping MSCP for that gave us 10 times the performance on SCP.
Okay, everything. Yeah. And this is very slow. And but actually, our solution is next slide like this. Okay, so this is the same environment, and we test it. So we are using this 1 terabyte data is. So now data is like this.
Also first.
So now we're trying to do 1 terabyte data from the one the BDM node to the other BDM node. But so the data is located in the placed on the DDN flash storage system. So this to this, so SSD to SSD. So data is like this. So I think that we have to send the data within the 19 seconds, almost 95 seconds, something like that. So anyway, we can get the so for measurement, we use the Boolean chart. So maybe we can use the we could use the other later measurement too. So anyway, this is so anyway, so no, this is actually what we did last week.
Is HCP public source, or is that something special, proprietary to you?
So HTTP.
HCP.
Yeah, this is actually from the solution by the Clearing Technology, Japanese company.
Okay.
Yeah, and actually, originally we just used the HCP, but we couldn't get better performance. So that's why we tuned the inside of the operating system so that we can take advantage of multi-threading.
Yeah.
So now, and also this HCP using the memory alliance technology. So anyway, so we are now working together from the storage side, network side, system side, and this is the result.
I'd be most interested in getting access to HCP if I could. Similar workflows. I think that's right.
So anyway, this is the for 19 seconds, I guess. And this is the 100 gigabits line. Right, so
Very good.
and now we are actually starting the negotiation with the department that have the biological sequencer that can read the protein base sequence of the protein and amino acid sequence of the protein or anyway, the sequence of the DNA, RNA, protein. So now we're starting the project. Okay, so and then so I think time is okay. So okay now so actually this we started this project a couple of days ago, and we have installed half of the electronic solution to our supercomputer system environment. So now we are trying to connect one or two departments to our computing infrastructure. After that, so I think user can enjoy the high user can perform the high supercomputing immediately after getting the data. So that is what we are trying to do. So in the case, actually, we can base the productivity of research happening in Osaka University. Anyway, so but we have to think about economy. So technology is okay, but actually we have to maintain the system and we have to provide user support. So that's why actually we have to get some money from the department. So we are that is thanks so much.
Thank you. Thank you for clarifying.
Yes, I think, the time is past.
Sorry.
So the question is, we have this
Yeah.
break time. And, I'm going to introduce the next speaker. Thank you. The release, the share. Attila, are you there?
Yes. Can you hear me?
Okay, Attila, the next speaker is, the UPM from Malaysia. And he's actually gonna, the presentation for the new HPC in the UPM and the update. Okay. Whenever you're ready and, start.
Okay. Okay. Hi everyone. Good morning.
Attila, turn on your microphone.
Sorry, Jemwood. Can you hear? Okay. Can you hear my voice?
How's the video getting out there?
Okay. Can I start? Okay.
Well, the reason why is because they're doing Zoom for connection, not HDMI. And it's
Okay.
a presenter.
Okay. Hi everyone. My name is Nur Asila. I'm from University Putra, Malaysia. So today I'm going to share on the updates on our HPC at our university. Thank you, Jong-hoon, for the introduction. Okay, so this
Don't
is
be on Zoom or mute and turn your audio. Yeah, there you go. Yeah. All good.
okay. Actually, we are hearing other
but-
voices.
The audio. Audio is
I
on.
don't
Were you only doing the audio from there?
Yeah, just turn the microphone.
Yeah, just turn it back on.
Just take the microphone away. Yeah.
Asila.
Yeah.
Why is everything
Yeah.
so different in this phone?
It's turn up.
Yeah, we still can hear voices.
Sorry, this computer is completely backwards. Audio, okay, that's output to here. This is turned on. Where's the audio coming in?
Audio coming.
Wait a minute.
Can you ask them to speak some more on the remote? I can't test if they're not speaking, unfortunately.
Attila,
Yeah, yes. Testing.
Okay. Okay, try again.
Okay, can I start?
Yes.
yeah, stop.
Thank
Okay.
you. Okay, so thank you everyone. So I'm Nur Asila from UPM University Putra, Malaysia. So today I just want to share about our HPC. I can see that just now from Osaka is very good. Maybe we are a little bit behind, but we are catching up. Okay, so this is our vision for UPM HPC. So we are expecting to establish University Putra Malaysia as a national hub for high performance and data intensive computing that advances Malaysia's scientific sovereignty, accelerates AI and emerging technology research, and foster a sustainable collaborative ecosystem to address national and global challenges.
Audio settings without it.
Okay, so this is our, in brief, our involvement in HPC. We have several other small HPC in other faculty also, but this one is the one that we share with everyone since 2012. So as you can see, in 2012 we have the one node HPC we have physical 8 nodes for 8 and in total 96. So this HPC basically serve as a grid computer from UPM and from Malaysia. And in 2015, we upgrade a little bit. Still, we just have one node with 64 core without any GPU. And this server also small, but it really contribute a lot in parallel and distributed computing subjects and research. And in 2018, we have one Tesla Volta V100. Although it's just one GPU, but it is very good where we managed to contribute for the AI, machine learning, and other related GPU research. And finally, in 2020, thank you to this APRP work group, TN and Asia Connect, we managed to have 3 nodes, 3 worker node, 1 master node with in total 144 for the worker node and 6 A40 GPUs. So with this latest HPC that we have, we managed to create like a HPC community for UPM. So we managed to educate and create awareness and educate all the users on using the software related to HPC, for example, like the Slurm modules and everything. So this is a number of users from various faculty and institute. And currently we have around 74 and it's coming. Actually, it's more where we also have like the undergraduate students during the semester open. So all these users running their project. And this is what I'm saying that with this server, we are ready to migrate for a new established HPC. So this is all the software that are currently in use. Okay, so it comes from many disciplines like the computational chemistry, bioinformatics, engineering, AI, and many more. Okay, so this is a very good news to us since we managed to secure our 12 Malaysian planning budget. Basically, we apply based on the obsolete 2012 HPC, and we managed to get around we managed to get, I think, yes, we managed to get around 500,000 USD, and we're expecting around 1,024 core with H200 GPU. So we expected to get it ready by end 2025. We are still working with it, but almost towards the end. We're expecting of 4 CPU nodes with 124 core in totals and 4 NVIDIA H200 with head and login nodes and scratch and user storage and other specification that we already list out for our new HPC. So we expected that this HPC will have this software environment as in brief, and will complement all the research demands from AI, bioinformatics, as what we can see from our current users. So right now, we have like Putra GPT, but we are unable to make it perform efficiently because of we do not have a very good GPU. So we expected by having the H200, it will improve this LLM project. Okay, and we also expecting to have like skill advancements and user readiness once we have this HPC, and we already have like a community of HPC for user empowerment to deliver comprehensive support for researcher at every stage. And then we going to have like a ecosystem development, so we can share all our research with and build a strong internal HPC team while cultivating a local community of experts to provide peer support. And we also planning to have a capability enhancement. So we're going to have a continuity and sustainable of a HPC expert. And we're also expecting to have a talent growth and knowledge sharings once we have this new established HPC. So thanks to this APRP project, because with this, we managed to create an interim HPC community where they may ready once we have the established HPC. We're also creating our website. We also have the website hpc.upm.edu.my, where all the resources, knowledge, and questions will address to this website, and everything is in charge from this website. So this is an example of current project, previous and current, that are running in our HPC. So our expected impact for the HPC is we increase research output, especially in AI and also in computational chemistry and bioinformatics, better collaboration opportunities. So once we going to have this HPC, we started to engage with the industry, where many industry in Malaysia, they are looking forward with the data intensive computing project. So this is like our good opportunities for us. And we're also going to create more HPC talent so that we have continuity and also sustainable in managing and continuing with the HPC research in coming years. So this is some example of our performance reductions with the APRP. As you can see, although we just have around 144, but we don't really allow everyone to use as a maximums. As you can see, so this one is reduced a lot. So once we have more, maybe it just going to have like maybe less than 1 hour to process all this execution, all this project. So we expected more HPC resources because right now Malaysia are looking forward with the AI and also the quantum computing. So there are more budget is open to have resources to conduct AI research. We also are hoping and looking forward for the Asian shared HPC from Korea, probably with high bandwidth distributed HPC capacity. So I'm looking forward to listen to the current update on this project of Asian shared HPC from Korea. And in terms of governance and sustainability, we expected to establish a dedicated HPC governance committee. So we are proposing these units, or maybe not really department units, to our research deputy vice chancellor. So we may have more human resource so to conduct, to maintain, to entertain all the users' requirements. And we will define clear roles and responsibility for all the system admin advisors and researchers. And maybe we will line out some policy and trends for our upcoming preparations for HPC, our future HPC. So a strategic move for UPM. So high performance computing is no longer optional. Although there is no excuse not to have, but we are looking forward for more. So we try to lead by example by investing in a scalable, sustainability, and future-ready HPC infrastructure for other Malaysian universities. And this initiative will boost UPM research excellence and global visibility, empower multidisciplinary collaborations and talent development, and support Malaysia's strategic goals in digital transformation, AI, and scientific sovereignty. So with this collective commitment, we can position UPM as a national HPC hub and a regional leader in computational science. So basically, this is our planning. We hope we will manage to have it and achieve it. So I guess that's all from me. Hopefully another next APRP meeting work group, I can share with all of you our new HPC server. Thank you, everyone. Thank you, Jong-hoon.
Thank you, Sila. And I don't know introduce next speaker. And the next speaker is the Sung Kim, and from the KIST Korea. He introduced about this building HPC infrastructure and HPC capacity for ASEAN data utilization. And also he in charge of this ASEAN HPC project. Sung Kim, are you ready? Yes, whenever you ready and start.
Okay. Hello, everyone. Can you hear me?
Okay, that's good.
Good. Okay. Good morning, everyone. I'm Sung Kim from KIST. I'm in charge of this project. This project name is Building HPC Infrastructure and HPC Capacity for ASEAN Data Utilization. It's a great honor for me to introduce this AKCF project today. I would also like to take this opportunity to sincerely thank all the distinguished guests for attending this event. And from the left, we have AKCF logo, and next KIST, and next BRIN Indonesia, and ASEAN. They are the key partners driving this project forward. Okay, let's begin the project introduction. Okay. To understand this project is essential to first comprehend the Cardiff project. Cardiff project was announced during the Korea ASEAN Summit in September 2023. The initial is Korea ASEAN Digital Innovation Flagship Project. The Korean government proposed the Cardiff project to strengthen ASEAN's digital capacity. This initiative was jointly proposed by the Ministry of Science and ICT and the Ministry of Foreign Affairs of Korea. Cardiff project is divided into three main components. First one is data ecosystem, and second one is digital capacity building, and the last one is AI convergence and spread. Our project belongs to data ecosystem number 2, building HPC infrastructure and HPC capacity for ASEAN data utilization. Our fund name is AKCF. AKCF fund initial is ASEAN Korea Cooperation Fund. That fund will contribute about US dollar 3,000 million, $30 million contribute this project. Okay, next slide, skip. And next slide show the status of the top 500 listed HPC in ASEAN. There are 6 HPC listed in top 500. First one is Singapore, is second one and third one is Thailand, and another one is Singapore. Singapore have 4 HPC in top 500 listed. Thailand have 2 HPC systems in top 500 listed. Okay, now I will explain this, our project. Our project title is Building HPC Infrastructure and HPC Capacity for ASEAN Data Utilization. Our project main goal is to build HPC-based data utilization infrastructure. Especially, we will install the GPU cluster systems in ASEAN regions. Especially, location is BRIN Indonesia. And we to reinforce ASEAN member states strengthen their digital competence. Our project final endorsed from September 11, 2024 in last year. Our duration is 4 years, and funding from the ASEAN Korea Cooperation Fund. Our budget is about US dollar $10 million. We have 3 project objectives. First one is building HPC infrastructure, especially about 3.5 petaflops HPC infrastructure for data and AI analysis. And the second one is science and technology knowledge platform. We will develop SNT knowledge platform to share national R&D information. And the third one is digital competence training. We will provide training for HPC and AI in ASEAN nations. Yeah, okay. First objective is building HPC infrastructure. This is perhaps the most critical part of this project, and its success is absolutely essential. First process is site selection. Site selection is completed by BRIN Data Center, Cibinong Science Park in Indonesia. And second, we are currently working on the design and the bidding. This progress is in progress. And third is HPC installation. Maybe it will be installed from January 2026 next year to June next year. We will build the infrastructure, and we will install HPC systems and conduct performance testings. And last progress is HPC operation. Now, let's look at the system design. To design this system in collaboration with the ASEAN HPC Task Force. This system will include 3.5 petaflops of GPU-based computing power and 3 petabytes of storage and interconnect speed of up to 400 gigabps. This HPC system will be shared by all 10 ASEAN member countries. Each country will remotely access and share the system through BRIN's data center. This means network speed is extremely important. To support this, I will continue working with Indonesia's IDRAN, which provides network support for BRIN to ensure both technical and policy level collaboration. Next slide is about building HPC infrastructure. We will design the facilities to install systems, storages, and network security equipment. The design includes at least 8 next space and 180 kilowatt of power and a system load of 3,600 kilogram. The required floor space is 32.4 square meters, and the cooling system capacity is over 60 RT. Next slide shows the BRIN's data center in Cibinong in Indonesia. We will, this HPC system will be installed in BRIN data center. On the right side, you can see the actual space where the system will be set up. Below that, you can see the UPS and the cooling systems. The next image shows the BRIN working on building the base infrastructure for the project. Second objective is digital competence training program. And we will train a total of 160 people over the 4-year period recommended by the 10 ASEAN countries. Participants will be nominated by ASEAN Secretary. Training will be conducted by KISTI's Science Data Education Center. This photograph showed the first training in KIST. Totally 20 persons from ASEAN member states. It was held 4 days from February 10 to 4th. 20 people joined this training program. And another photos. And this photo showed the kickoff ceremony in Jakarta, Indonesia on March 10 in this year. Okay. This the most important part of project management structure is cooperation with partners. In particular teamwork between ASEAN HPCTF, KIST, and BRIN is the top priority. Project steering committee oversees decision-making, provide guidance, and ensure project governance. It includes the ASEAN Secretariat, AKPMT, Republic of Korea Mission, and KIST. Last slide showed the project implementation plan in 2025. We will present the key project implementation plan. First is HP system procurement process in July, from July to September 2025, and we will build our HPC infrastructure at Green Data Center. This progress is in progress. And the third one is building of a science and technology knowledge platform. And in this year, we will train the second training program on October. And most important is to interconnect to international network connectivity. It will be up to 10 gigabps in February 2026. And after HPC system procurement process, we will deliver to Indonesia HPC systems. It will be on February to March 2026. And it will be implement HPC system at BRIN until May 2006. And after that, we will have the opening ceremony on May or June. Okay, that's all. Thank you very much. Thank you.
Thank you, Dr. Kim. And the next presenter is the Columbus Sapphire for Cancer. So, and I will prepare the presentation my son. And wait a minute, I add June. Okay, today the APAN60 one is the last presentation, and I wanted to say that ASEAN Pacific Research Platform activities, working group activities, and the related work including the CDK project and the Korea Research Platform. All this content, every APAN meetings, whatever, a little bit upgrade, update. And this is today's agenda and about APAN, APAN working group, and the CDK collaboration project, and last one is career research platforms. The overview of the APAN, the APAN working group initiative is since 2018 in Singapore, and our objective is to how to promote the distribute the share the HPC ecosystem in ASEAN Pacific areas. The second thing is engage the APAN members and the ASEAN countries. And the last one is toward the setting up to the ASEAN Pacific Research Platform and become a part of the global areas. the global community name is GRP, the Global Research Community, the executive member, and we have the two the international collaboration project. The first one is Asia Connected project is finished 1.5 years ago. And the second thing is A347 project, program project. It started last year in August. And I wanted to add in the one. All those technologies comes from the NRP, National Research Platform. The National Research Platform and the formal project name is the PRP, First Field Research Platform. The First Field Research Platform is supported by the 2015 by NSF. They wanted to deploy the high bandwidth distributed HPC, even though in US they don't have not enough. They don't have IT resource to support a service for their the researchers and the students and the universities and so on. So the researchers and engineers is the focus on the high bandwidth. It means that it's over the 100 gigabps, and the high bandwidth is cross point, and they set up this DTN and the HPC or the super facilities, and they share and some IT servers and some IT resources a little bit donated to bring this high bandwidth network and to gathering and through this Kubernetes or the MPI or the parallelism solutions and make the big one thing to the delivery to the user and the researchers. And API is kind of the Asia versions. And we have it 2 times in a year, and every day APAN meetings is the last APAN meeting is the 58th at Islamabad, Pakistan, and we have 2 sessions and 10 presentations from the 6 countries. And at that time, it's the remarkable topic is the quantum network by Dr. Raz Ketmus. He came from the Argo National University. And this is the briefly introduces the to what the contents is presented at that time. And this is the last APAN meeting is the 59th at the Yokohama in Japan. And we had the 3 sessions, the keynote speech and the application and the country update and the technology, the technical part. And 12 presentations is from the 8 countries. Its main topic is wireless, science and DPN and the AI and the bioscience and the NRP experience. And the gene editing and the seeders research from the medical areas and the research platform for agriculture and the shared storage and the multi-domain and the data storm of data and so on. And this is the other program. It's the last APAN meetings and briefly the status at and I wanted to talking about this CDK collaboration project in the Northeast Asia. And the main the countries is Korea in the Korean and the KISTI, and in case of Japan, the Riken Institute and Osaka University. And the third one in China is Guangzhou Supercomputing Center and the Sun Yat-sen University. Duration is 5 years in the bodies like that. There's each country's PI, the Yutong Lu from China, and Kaneyama Hidetomo from Japan, and me from here. And we, I'm missing one slide. And we, this project is a strategy is divided into 4 units. The first thing is infrastructure unit. The second thing is data transfer unit. And the third is data compress, and the fourth is metadata unit. The project is focused on how to share the HPC like or the high IT infrastructure Northeast Asia, the focus on the Korea, China, Japan. And you know, there's the Guangzhou Supercomputing Center is they have the Tenor 1 and Tenor 2. The Lincoln Institute, they have K computer and Fugaku computer. And the KIST is Korea, the representative supercomputing center. The first stage, and we done the survey for this, how to the communication, how to the connection with the Northeast, the three countries. And all this technology and all this is the researching is focused on to how to make this international open science. So the KIST part is the data transfer unit, and this part is related is the APRP in APAN and the KRP and NRP and GRP, and we can call it XRP. And how to set up the science DMZ and how the accelerations is for long distance data transfer and the building mutual trust and the secure transmissions. And we just heard from this the professor Tate and Osaka University already set up the GTN and the file system, and he demonstrations on the using SCP or the edited SCP and blah blah. And all those technologies comes from this NLP or how to big data transfer. And the first speaker is Dr. Kim, and he mentioned the index project. He gonna to make this high throughput between data centers in Korea. And the second unit is data transfer issues is very important. But currently the international network status is upgrade and upgrade, update and update. Currently, we can share to make this spatial line. And it's kind of the idea to separate the business traffic and the data, scientific data. We can deliver in the high throughput network, even though using the InfiniBand or some the local lines or the internal the network technology expanded to this globally. It seems like it's a LAN or something like that. This is KIST's strategies. They want to start building and installing and measuring. And this is the same things include. And in particular is in case of Korea deploy third-party applications. And it's just not the paperwork, and we want to make the actual deploy. And our research build AI, biomedical science, the weather and climate, and some related physics and the data intensive science. And the last 1 year, and we focus on and develop for the disaster and the agricultures and related the weather and climate data, how to gather the spread is the diversity data, how to make the generation, how to the running their models on the research platform. And we just starting the stage, what kind of data and how can we gather the receiving or the managing. And this is the very the simple showcase is urban flooding research. And this is some special areas is on when this the heavy rains in Korea. Some I'm not sure this is the some part of in the Seoul, and the red color is very the big disaster areas. Is how to the forecast based on the climate and weather data and running on this distributed research platform. And this is the how the website is the hardware requirement, and the right side is the models is how many models or what kind of models are running on this platform, and what kind of models is focused on the domestic scientists. And this is the second our the research topic is AI-based network intelligence in Korea. We're gonna deploy the AI technology. So But the first stage, it just the topology is just a pseudo topology. Korea, China, Japan. It's a what kind of the AI technology is possible to and proper to the northeast, the three countries is interconnected. And the last item is Korea Research Platform. And the Korea Research Platform, we have already 25 is government funded the National Research Institute. So since 2015, we became the global partner of PRP and NRB project. Currently, we have one GPU node and one CPU node donated the National Research Platform and the big and the platform. And since 2018, we started the APAN APRP working group. And since 2021, expanding to the 7 Korea Research National Research Institute. And 2022, and ASEAN Connect project started 2024, and A3 collaborative international project. The Korea KRP's national scale is final goal is establish a high reliability and high speed transfer system without boundaries between participants. Many institutes, they have on the security layer or the security environment. Even though the Korea and we against the North Korea and the Korea CIA is bearing the heavy pressure to make the security environment. So it's not easy to share independent institutes to communicate with the other neighbors, even though neighbors. So we wanted to make this get rid of this firewall or the security equipment through this drop the zone. And it's kind of the policy issues. And we can make the drop the zone each other in the non-participant institute. And we release this firewall or the integrations, the security policy and the network performance is rapid up, going up at that time, and we can share all super facilities and all data centers and all the research peoples. So this is our final goal. And this is the key in the resources, the GPU centers and supercomputing centers and the data centers. And I will say this is the other word is HPC over HPN. HPN is a high performance network, a high bandwidth distributed HPC. And we wanted to deploy the faster workflow with the big data for our customer and our the members in Korea. And this is a small the architecture and the KRT Korea Research Platform. This is internal architecture. We just organized this system is the 4 or 6 server, and we deploy the Kubernetes and managing our engineers. And we made the portal for the Korean user, and we're using and open sources like that. And this is the showcase our the related the project in Korea. The first thing is the smart agriculture, and the smart agriculture is this side is the smart agriculture researchers want to running their models on the high performance platform or high performance computing, but they don't enough IT resources, and but they can access through the high speed network, and they deliver their data and they're running their the crop model or the weather model on this platform. And the right side is how can make this the ensemble environment. The ensemble meaning is they said that the model A and the make the result, and this result is put in, and the model B is input data. And this is an ensemble environment. They want the several models running at the same time, and the original result. So they just step by step running their models, but that is very slow and stupid. So this infrastructure or technology when the service for their area and their researches is going up and make the reasonable result. And this is a smart decision-making system. As a whole, the project is focused on when some disaster situation, typhoon and heavy rain, or some such like a disaster. So when the government officials, he should declare this is disaster or not disaster, but it's a very big high responsibility on their mouth. When someone is not declared disaster, but many victims occurs everywhere, it is those things is responsibility for the government officials. So this system is put in the several models from the weather and from the what kind of things from weather and the flooding or earthquake or the several the disaster or the national the changes model and putting this platform and running at the same time and they want to use it and this result to decision their system. So we just advisory and support these solutions you can use to use the HPC or the running models. And this is the medical areas. Some our the Korean medical university, some the expert the students of medical using the this whole NLP system and distributed system. He researches for the gene seizures research areas. And at this item is the more detailed explained is a session 2. And student is Min Kim and gonna present it at the same session 2. So anyway, and all those kind of the contents is should upgrade every time, every meet, whenever we meet again, and expand the tool, this infrastructure to ASEAN region, and then the activated of the APRP and how to discover the third-party research areas based on the HPC-based areas. In particular, in case of the UPM, the first APIP, the research platform, already set up the UPM University for 4 nodes, and the master node is 3. GPU include this worker model. And ASEAN HPC, the project is the funding by this Korea, the Foreign Affairs, and I already suggested how do you share your HPC resource or the HPC performance to member countries. As you know, this the ASEAN countries consist of 10 countries. And 10 countries want to use it, the whole capacity HPC, but time sharing and scaling is very important. And also the high-speed network is very important issues. Their timeline is the bottom of 3 or 4, and they establish the international resource network, and they have the education, but that includes how to share the CPU or GPU resources. So at the time, and we can support comment over our ideas. So thank you for listening. There is a session 1, and I want to finishing the session is 7 minutes over time. And we take a break time and the session again, and 10:45. 10:45, yes, and we take a break time, and whatever you have the questions, and the previous talking is a break time. Thank you for joining this API working group. Thank you.